Hey, welcome back to Calculus. In this last section of Chapter 4, Section 4.9, we're going to take a look at something called antiderivatives. I've got the learning objectives for the lecture up there. I'll let you look at those and just skip right down to the motivation. That I was telling you earlier that calculus is the mathematics of rates of change, and the reason why scientists from all different disciplines take calculus and learn calculus is because scientists are basically people who are interested in observing how quantities change and trying to say something about what the quantities are. So when you're out collecting data in your various disciplines, you're collecting data about rates of change. You're collecting data about a derivative. And from that derivative, you want to be able to say what the function is. So you're in this position where you want to be able to start with a derivative and say, well, what was the quantity that would have that derivative? And that process is called anti-differentiation. That's why we're bringing it up right now in our course. Let's make a formal definition and look at a couple of examples. So I'm going to call a function capital F an antiderivative of little f. So capital F is an antiderivative of little f if the derivative of capital F is equal to little f. All right? So let's look at a couple of examples. Capital F equals sine x is an antiderivative for cosine. Why? Because the derivative of sine is cosine. Right? So if the derivative of capital F is little f, then capital F is an antiderivative. Capital G equals x cubed over 3 is an antiderivative for the squaring function. Why? Because the derivative of x cubed over 3 by the usual differentiation rules is the squaring function. Notice that capital G1, I'm going to give it a slightly different name. G1 is x cubed over 3 plus 7. That's also an antiderivative for the squaring function. Why? Because when you take its derivative, well, you'll get the x squared from the x cubed over 3 part, and the derivative of 7 is 0. So it also has this derivative. So it's also an antiderivative. So unlike differentiation, a given function, if it has a derivative, it only has exactly one. A given function can have more than one antiderivative, yeah? X cubed over 3, x cubed over 3 plus 7 are both antiderivatives for the squaring function. In fact, that's kind of the only way antiderivatives can differ. This is a result that we're going to just kind of bring back from chapter 3 here, but the theorem is that if you're an antiderivative for a little function, then any other antiderivative is that particular one plus some constant. Yeah. So what's the proof of that? Maybe you remember back in chapter 3, I'm just going to be sort of brief about this so it doesn't take too long to write, that if two functions have the same derivative, f1 and f2, then they differ by a constant. f1 has to be f2 plus c by the mean value theorem. Was one of our consequences of the mean value theorem. Well, any two antiderivatives for little f certainly have the same derivative. Those derivatives are both equal to f. So any two antiderivatives differ by a constant. It's a consequence of the mean value theorem. And then certainly any two functions that differ by the constant have the same derivative. So they'd be antiderivatives for the same function. All right. So this is kind of this notion, this general antiderivative is what I want to define. When I speak about the general antiderivative of a function, I don't really mean just one function. I mean a family of them. A family of them, it's any particular antiderivative plus an arbitrary constant, okay? So the general antiderivative of a function, little f of x, it's not a single function, it's an infinite family of them, but any two members of that family are just, they differ by a constant. Their graphs are vertical shifts of each other. So just to get you used to the language here, let's go back to those examples. If I want the general antiderivative for the cosine function, I would say, well, it's sine of x plus c, where c is an arbitrary constant. That's the entire infinite family of functions whose derivative could be cosine. Yeah, the general antiderivative of the squaring function is 1/3 x cubed plus c. C is an arbitrary constant. Any antiderivative of the squaring function has this form for some number c. All right, so a particular antiderivative is just a function that has the derivative little f. The general antiderivative is a particular antiderivative plus an arbitrary constant. Okay, so some vocab to get down. Let's talk about how I found that antiderivative for the squaring function. We can actually, let me just reveal all of this. Uh, if you take a power function, since we know how to differentiate powers, right? When you differentiate a power, you bring the power down and then subtract one from it. Well, so to anti-differentiate a power, we should just reverse that. Yeah. So to find an antiderivative for x to the n, what should we do? If we do those steps in the opposite order and reversing each step, well, we would add one to the exponent. Yeah. So that's the opposite of subtracting one. And then we need to divide by that new exponent. This is why n can't be minus 1. If n is minus 1, I'm dividing by 0. So this is how you find the antiderivative, the general antiderivative of any power of x. You increase the power of x by 1 and divide by that new exponent. Well, any power of x except for the negative first power. Here I've just got a little proof of it. Look, anytime somebody's saying a statement like the general antiderivative of some function is something, you can always check that. Differentiate the something. All right, so I'm just walking you through the differentiation here. The derivative of a sum is the sum of the derivatives. Put a constant out front. Here's our power rule. I took n plus 1, I brought it down, I lowered it by 1. The derivative of c is 0. 1 over n plus 1 times n plus 1 is 1. So there you go. When I differentiate that function, no matter what c is, I get x to the n. That's the general antiderivative. You can combine that anti-power rule with the fact that antiderivatives, like derivatives, can be taken term by term. What do I mean by that? If I have a sum or difference of functions, I can just anti-differentiate each one of them, taking the sum or difference, because that works for derivatives. Same thing with constant multiples, right? Not products and quotients. You guys know the product and quotient rule are more complicated, but for sums and differences and constant multiples, you just do them term by term. Well, antiderivatives would be the same, because the differentiation rules work that way. All right, so let's check out an example. Maybe I want to find the antiderivative for a polynomial function like this. X to the, it's not a polynomial function, excuse me. It's x to the fourth minus 2x squared plus secant squared. Okay, so I'm going to do this term by term. So finding an antiderivative for it, I'm going to call it capital F of x. And what am I doing? I'm looking at this first term, x to the fourth, that's a power. So our new power rule says that I should add 1 to that exponent. So I get x to the fifth, but then I have to divide by that new exponent so that when I differentiate that power, the coefficient cancels. So stop the video for a second and just check that if you differentiate 1/5 x to the fifth, you get x to the fourth. All right? So now I'm just going to move along to the next term. The next term has a constant multiple, minus 2. Well, I'll just put that same constant multiple in the derivative. And now what do I anti-differentiate? The x squared. All right, so using our power rule, I have to increase that exponent by 1, and I have to divide by the new exponent. So again, if you check with differentiation, the 3 would come down, canceling the 1/3, the minus 2 stays there. That term's derivative would be minus 2x squared. The last term looks scary, secant squared. Remember the question we're asking. So I'm asking, I need a function whose derivative is secant squared. So if you've practiced your differentiation a lot, I have good news for you. Your anti-differentiation skills are going to be strong too, because just ask yourself out loud, stop the video. Do you know a function whose derivative is secant squared? Have you ever differentiated something and gotten secant squared? Yeah, you have, and me too. It was tangent. The derivative of tangent is secant squared. All right, so our directions were to just find an antiderivative for this function. So there you go. And you can check it. You can always check an antiderivative problem by differentiating. Just take the derivative. When you take the derivative of this thing, well, 5 times a fifth is 1, and you get x to the fourth. 3 times a third is 1, so you get minus 2x squared. The derivative of tangent is secant squared. All right, so just like derivatives, antiderivatives can be done term by term. And you've got this power rule. Anytime you know the derivative of something, you know the antiderivative of something else, right? Like because I knew the derivative of tangent, that means I know the antiderivative of secant squared. Cool. Let's try it again. These are just examples like that. Here I'm asking you find the general, so we'll add our constant antiderivative for 1 over x. So do you know a function whose derivative is 1 over x? Sure you do. It's the natural log. And in fact, remember, to expand the domain, we said it could be the natural log of the absolute value of x. So I'm not calculating the answer to this example. It's something I know. I know the derivative of log of absolute x is 1 over x. So I know that antiderivative. How about this one? The square root of x. The square root of x is just a power. It's the 1/2 power. So it's antiderivative. We have to go a little slower here, maybe. You have to take that 1/2 and add 1 to it. And then you have to divide by that new exponent. Yeah, you can certainly do that all in one step. 1/2 plus 1 is 3/2. So it's 1 over 3/2 times x to the 3/2. But 1 over 3/2 is kind of an ugly way of writing 2/3, right? It's the reciprocal. And we wanted the general antiderivative everywhere. So shame on me. I should have been adding c to all of these things. So there's our general antiderivative for the square root of x. It's 2/3 x to the 3/2. Check it. Stop the video and check it with differentiation. Cool. Here's just a little table kind of illustrating some of what we just did and what I was just talking about. Where should we start? Like here, so in this table, there's two kind of tables here, and the author's listing functions in the left column, and then particular antiderivatives. So one of the ones we just talked about was this. The antiderivative of 1 over x is log of absolute x. E to the x, notice, is its own antiderivative. Here's our power rule. The antiderivative of x to the n, if n is not minus 1, is equal to x to the n plus 1 over n plus 1. Notice this is the n equals minus 1 case. So you do know how to antidifferentiate all powers. We did this one above. The antiderivative of cosine is sine. So in all these cases, we did this one above. The antiderivative of secant squared is tangent. Stop the video and explain this to yourself. Why is the antiderivative of secant times tangent secant? And so on. All of these are just differentiation formulas that we learned in the past. If you take anything in the right-hand column in these two tables and you differentiate it, differentiate the thing on the right, you'll recover the thing on the left. That's what we mean by antiderivatives. Okay. All right, this video is getting a little long, but I want to tell you something about differential equations. So going back to my spiel, scientists are basically people who want to solve differential equations. They want to look at some rate of change and recover the function. So let's look here. So I'm saying let's find a function f of x such that its derivative is 5 times x to the 2/3, and I want that function to satisfy f of 8 is equal to 21. Okay, so if I was out observing data, maybe for some reason in my data observations, I know that the quantity I'm interested in is changing like this, and I measured when x was 8, the output was 21, and I'd like to be able to recover the function. So the first statement is called a differential equation. It's an equation in an unknown function, and it involves its derivatives. So the solution to a differential equation is not a number, it's a function. This second thing is called an initial condition. It's just some value of the function at some point. Okay, so we're solving a differential equation subject to that initial condition. Well, if we want the derivative to be 5 times x to the 2/3, well, then we should antidifferentiate. So our function should be, I'm just going to use our rules as we go. 5 is a constant multiple. X to the 2/3 is a power, so I'm going to add 1 to 2/3. 1 is 3/3, so if I add that, I'll get 5/3. And then I need to divide by 5/3. I prefer multiplying by 3/5. All right, so there's an antiderivative. If I add an arbitrary constant, that's a general antiderivative. And I can clean that up a little bit because 5 times 3/5 is 3. So there's sort of the general solution to our differential equation, but we're going to use this initial condition to determine the constant. Yeah. So what does that mean? The initial condition tells me that when the input x is 8, the output f of x is 21. So 21 must be what I get when I replace x with 8. Okay? So I'll leave it to you to check that the 5/3 power of 8 is 32. 32 times 3 is 96. So if you subtract 96 from both sides of that equation, I'm moving fast. I hope I don't make a mistake, but I'm getting c is minus 75. Okay, so our solution, the solution to our differential equation is this function, f of x is equal to 3 times x to the 5/3, take away 75. And I'm going to leave it to you to check, and I hope you'll stop the video and check it, that the derivative of that function is indeed 5 times x to the 2/3. Stop the video and check it. And if you plug in 8 into that function, you will in fact get 21. All right? So that's solving a differential equation subject to an initial condition. Let's do another one. Differential equations can have they can involve higher order derivatives. This is a second order differential equation, or people usually in this business just call differential equations DEs. And we have two initial conditions. The function's value at 0 should be 4, and its derivative should be 12. In general, you need an initial condition for every order of derivative. If you have a differential equation with second derivatives in it, you need two conditions because each condition will determine one constant. Okay, so to solve this thing, this second order differential equation, we kind of have to anti-differentiate one step at a time. So if the the second derivative is that polynomial, then its first derivative should be an antiderivative for it. So I'm going to go a little bit faster here so the video doesn't get too long here. So I'm going to simplify as I go, but I'm anti-differentiating that polynomial term by term. I'd have to get something like minus 2x. Then using the power rule, I would get 6x squared. And using the power rule again, I'd get minus 4x cubed. So all I did was just simplified the coefficients as we go, but I have to add a constant. All right, because that derivative is only antiderivative is only valid up to a constant. And now I'm going to use this initial condition that when I make x 0 in the first derivative, the output is supposed to be 12. So 0 plus 0 minus 0 plus c, that means that c has to be 12. Okay, so we've recovered our derivative. Our derivative is negative 2x plus 6x squared minus 4x cubed plus 12. And now from that derivative, if we anti-differentiate again, I can recover the function. Yeah, so I'm looking at this derivative using those power rules. So again, I'm going to do this kind of quickly, stop the video and do it at your own pace. But if I anti-differentiate term by term, I should get something like minus x squared plus 2x cubed minus x to the 4th plus 12 times x. Yeah, should I stop for a second? An antiderivative for 12. What function would have derivative 12? Well, 12x. 12 times x to the first power. But I need to add a constant. I'm just going to use the same variable name. I don't have to keep renaming it. And now I'm going to use the second condition, or the one I listed first, that when I plug 0 into f, then I'm supposed to get 4 as an output. So 4 is 0 plus 0 minus 0 plus 0 plus c. So c has to be 4. So we can write down our solution. Our solution to the differential equation is f of x. I'm not going to try to reorganize these terms. I'm just going to write it as I see it. Minus x squared plus 2x cubed minus x to the 4th plus 12x plus 4. So once again, I would strongly encourage you, I don't know if I can show you all this at the same time, I would strongly encourage you to check this, to check that that function that I just boxed right there has second derivative equal to that quadratic polynomial. Check that when you plug 0 into it, you get 4, and when you plug 0 into its derivative, you get 12. Okay, so we're solving differential equations by anti-differentiation. Getting near the end of this, what's getting to be kind of a long video, I just want to talk about the application of this business to motion along a line. All right, so maybe you want to pause and get your breath back or something if you're feeling tired, but I'm just going to keep going. Talk about motion. We already know that the derivative of a position is the velocity, and the derivative of the velocity is the acceleration. So it therefore follows that if you anti-differentiate acceleration, you get velocity. And if you anti-differentiate velocity, you get position. So you can recover the position of something from its acceleration or its velocity by the anti-differentiation process. Those antiderivatives will involve constants, and you'll need conditions. You'll need either an initial velocity or an initial position to recover those constants. So let's just do one example. And I think this one I maybe have written it all out so we can go a little bit faster here. But let's check it out. So near the surface of the Earth, under some simplifying assumptions that I'm just going to make, the acceleration due to gravity of an object in free fall is a constant. Okay, and that constant is approximately 9.8 meters per second squared, and I'm going to call the acceleration negative, building in a sign for the direction. Okay, so the acceleration of an object in free fall near the surface of the Earth is negative 9.8 meters per second squared. Take it as a given. And then let's say we throw some object, a stone. We throw it upwards with an initial velocity of 10 meters per second, and we do it from a very tall tower, a 100-meter tall tower, okay? And what I would like to do is recover the height, recover the position of the object t seconds after we throw it, okay? So we're gonna anti-differentiate. Let me just show you a little bit at a time here. So the velocity function. The velocity function is an antiderivative of acceleration. Acceleration is a constant. So the antiderivative of negative 9.8 is negative 9.8 t. The variable is called t, not x. Well, plus some constant. But using this initial condition, we were told that we threw this stone up with an initial velocity of 10 meters per second. So that's telling us that v of 0 is 10, okay? Here I want to remark actually that because the positive direction is upwards, it's 10. If we had thrown the stone down, yeah, if I had written that we threw it down at 10 meters per second, I would say that v is negative 10. So we're using that same convention and sign that we do in our motion. Up is the positive direction. So if we throw it upwards, the velocity is positive 10 meters per second. So if I put in positive 10 for v and 0 for t, I recover that c is equal to 10, and that gives us our velocity function. Okay, so we've recovered velocity from acceleration and the initial velocity. Cool. How do we recover position? We do it again. Position is an antiderivative for velocity. Okay, so what am I doing here? I'm taking term by term, negative 9.8 t. I'm adding 1 to the exponent, t squared, dividing by that new exponent. Negative 9.8 over 2 is negative 4.9. Derivative of 10t is 10, so the antiderivative of 10 is 10t. And then I have to add a constant. We were told that we threw this from a tower that's 100 meters tall, okay? So that means that s of 0, our initial position, is 100. So down here in our calculation, if I let s be 100 while putting in 0 for t, I recover the value of c. Turns out it's 100. All right, so we've recovered the position function from the acceleration, the initial velocity, and the initial position. Cool. We'll have a chance to practice some more things like that on your activity. This video is getting kind of long. I'm going to end it here, but I'm just going to kind of show you. I'm not going to answer them, but these are examples of related questions that I could ask you about this kind of business. And you can answer these questions. I hope actually you're going to do it. I hope you're going to take this function s of t and answer these 4 questions, or come to an office hour and talk to me about it if you want to. But I could ask you things like, for example, what's the maximum height that this stone is going to reach? How far off the ground in meters will this stone get to if we launched it up at 10 meters per second from 100 meters? When will it reach that height? When's it going to get there? Another question I could ask you is, when's the stone going to hit the ground? Right? We throw it upwards with 10 meters per second. It's going to reach some maximum height, and then it's going to start falling. It's going to hit the ground eventually. When's it going to hit the ground? Yeah. What's the velocity at that moment? What's the exact velocity at the moment it hits the ground? Those are just some questions that we could ask about this. Okay. Well, I hope this was useful, and thanks for listening.